Well, good afternoon and welcome to our first Intersection of Challenge and Change panel series. And I'm pleased to welcome you on behalf of United Way of Greater Lafayette. My name is Jay Ackridge. I serve as Provost and Chief Diversity Officer at Purdue University, and I'm also a member of the Vanguard Committee. I know that we have a number of Vanguard donors with us this afternoon for this event, as well as other members of our community. And I just want to say a special thanks to our Vanguard donors for their support of United Way. I had the privilege of serving as community chair several years ago, and I know how important Vanguard donors are to the success of the community campaign. And certainly we all know this year in this time of COVID-19, how important this community campaign is to our community as COVID-19's presented challenges for all of us, but especially those in need. And we just appreciate your ongoing support of United Way, and especially this year. This panel series, there'll be 4 of these events, and you'll be getting notifications on those. This one today, focused on COVID-19, the science behind the virus. On September 16th, bringing hope to housing. On September 23rd, building blocks of basic needs. And September 30, the position of public service. So we hope you'll join us for future change and challenge panel events. But this afternoon, I'll have the privilege again of serving as your moderator for our discussion, and you'll have a chance to send some questions. But we really wanted to open up the science behind COVID-19, and very pleased today to have a distinguished guest, Dr. Richard Kuhn from Purdue University. I'm going to be unfairly brief with his introduction so we can spend as much time as we possibly can with him this afternoon. But Dr. Kuhn serves as the Trent and Judith Anderson Distinguished Professor of Science in the Department of Biological Sciences here at Purdue. He's also the Krenecki Family Director in the Purdue Institute of Inflammation, Immunology, and Infectious Diseases. He is a structural virologist and world-renowned for his work in that particular area. His work focuses on model systems in particularly challenging diseases, dengue, West Nile, and the hepatitis C viruses. And some of you would recall in 2016, he led the team that determined the structure of the Zika virus, a really important breakthrough in that particular disease. So many these viruses are all RNA viruses, and he focuses on the interaction of the virus and the host. And of course, the coronavirus that causes COVID-19 is a RNA virus, and certainly makes him in extremely high demand, especially over these past few months as our world has dealt with COVID-19. I know it gets calls from everywhere, but I think the first call President Daniels made when COVID-19 became an issue on our campus was to Richard. And if I recall correctly, I think he was in Southeast Asia at the time leading a program on coronaviruses. And so, again, we're delighted to have him with us this afternoon to talk to us about some of the science behind COVID-19, especially as we start to think about treatments and vaccines going forward. Our format, he's got a few slides to present this afternoon, and then we will open it up for questions and answers. I've got some questions some of you submitted prior, but we'll also be taking some questions from you as we work through the session. So let me turn things over to Dr. Richard Kuhn.
Well, thank you, Jay, for that introduction. And I really appreciate the opportunity to come to talk to you all today about this virus that has turned our world upside down. I also just want to say thank you to all of you who support United Way. I think, as Jay mentioned, it's always an important thing to support our community, but even more so in this time of crises. So, Kofi, if you can give me the first slide. And let's just go to the second slide right away. So this slide really is something that probably you're all aware of. We want to make sure that we prevent you from getting this virus. And so the panel on the left is very important. These are fairly simple things to do. They might take us out of our normal lifestyle. But these are things that you've heard over and over again. Social distance, wear a mask, wash your hands. These are really important things. Unfortunately, some of us will be in a situation in which we are exposed to the virus. and we may get sick with the virus. And so you're all familiar with the symptoms. It's been widely reported. Kofi, do you still have the slides up? Okay. Well, then let's go, since you all know those symptoms, I want to go to the next slide and just tell you one thing that you may not be aware of. Next slide. So this is what we call the iceberg principle of pathogenesis. Pathogenesis being disease that humans or animals, even plants have. In most viral infections, very few individuals normally get disease or get very sick. There is usually, it depends upon the virus, but there's usually a large fraction of people who don't show any true symptoms. They may feel slightly different, but they may not recognize themselves as having a disease. West Nile, for example, 80% of the people who get West Nile don't know they've been infected with West Nile. And only 1 in 150 of those people who get infected with West Nile actually come down with the symptoms that's associated with West Nile, that is encephalitis. And so for COVID-19, this pyramid is a little bit different in that probably a greater percentage of people show symptoms, but it really depends, as we all know now, on the age group. The younger folks don't show symptoms as much as the older, or not even older, but middle age and older folks. That doesn't mean that they're not infected. It just means that they don't show symptoms. So let's go on to the next slide. So this is just the transmission cycle. We really don't know, if you look on the left side, exactly the origins of what moved the virus, what was the intermediate vector for giving it to humans. The origin of a lot of these coronaviruses and SARS-CoV-2 probably does come from bats, but we don't know what that intermediate host is. But that intermediate host did pass it to humans. We don't know how many times, but once it established itself in the human population, it was able then to move from human to human. You can have an animal transmitted to a human, and it may stop there. It may not be transmitted from that human to another human. But in this case, it has happened, and now we have human-to-human transmission. And on the right side of the slide, we just see that since it's a respiratory virus, this virus is predominantly passed through droplets, possibly through aerosols, possibly through environmental contact. Respiratory viruses have the potential to spread very rapidly in a population, like measles virus, for example. Next slide, please. The interesting thing about COVID-19 is that it seems to attack many systems in the body. Some viruses are very specific. Hepatitis C virus, for example, infects primarily the liver. That's why it's called hepatitis virus. But COVID-19 appears to attack many different organs in the body. And that makes it very challenging in terms of treating a virus like this. Certainly it hits the respiratory tract, but there's also examples of it affecting the brain, liver, and the gastrointestinal tract. And it's not clear, it may also be able to infect through a gastrointestinal route. Next slide. We know a lot about this kind of virus because we've seen it before. And although we don't have what we call a very high resolution picture of the virus, this schematic on the left side really highlights what it is. It basically is a molecule of RNA surrounded by lipid and proteins. And the important thing that Jay mentioned to begin with is that it is an RNA virus. It's not a DNA virus. That gives it certain added features, but it also gives it some added subtractions. Next slide, please. So human coronaviruses have been around for a while. The first one that we really were very interested in was the predecessor of SARS-CoV-19, that is the original SARS virus, which appeared in 2003. And then in 2012, another highly pathogenic human coronavirus appeared, and that was called MERS. And now in 2019, we have the appearance of SARS-CoV-2. But there are other coronaviruses that infect humans. Many of these we've probably been infected with, that cause very mild respiratory disease, very similar to what we would get with the common cold, which is normally attributed to rhinovirus, which is another very different type of virus. Next slide. So an important question is, why didn't we see this virus coming and be prepared? We have a lot of technologies. Well, for many years, many of us, Bill Gates being one of the primary people who had a big voice, said we need to be prepared. We weren't sure what type of virus we'd see. A lot of people did expect it to be the flu virus. And I don't want to scare anybody, but it's going to happen sometime in the next few years that we will have a flu virus that is going to be of this kind of significant pandemic effect. And so that's why we're very worried about the flu season this year. Indications from the Southern Hemisphere suggest that the flu season may not be as bad. We don't understand the science behind that. But right now, it doesn't look like the flu season will be bad. But we cannot take that chance. And so it's really important for all of you to be vaccinated against the flu. But the flu certainly will cause a pandemic like this sometime in the near future. But there are many possible viruses that can cause this kind of pandemic. And so figuring out in advance which one it's going to be is not as important as it is to be prepared. And I'll talk a little bit about that in a little bit. Next slide, please. So the importance of this slide, this is just highlighting a whole series of different coronaviruses with the human coronaviruses listed in red. The important point here is these viruses are all coming from animals. In this case, a lot of it is coming from transmission from bats, either directly to humans or through intermediates. This is a major problem, and this is the source of future pandemics. These are what we call zoonotic viruses. They move between animals and humans. And we have tools in which we can monitor this. So I think the answer to, can we predict this in the future? We can predict that things are coming. We might have an early surveillance system, but we won't know exactly which virus is going to come. Zika, of course, was a virus that we didn't expect Zika to be the pandemic virus, but we knew these types of viruses, flaviviruses, were capable of this kind of an outbreak, a pandemic. Next slide. So how are we going to deal with this? There are two basic strategies that we normally think about. One is vaccines. Vaccines are meant to, they're given before you are infected with your pathogen, your virus. Okay, and they're meant to protect you against getting disease. However, if you get disease, then hopefully there might be some strategy, some drug that you might get, some therapeutic. So that's the second part, the therapeutics. Now, vaccines can also be given after infection, and therapeutics can be given before infection. But most of the time, vaccines are given before, therapeutics are given when you're infected. Next slide, please. So the vaccine is a substance that's used to elicit immunity from your normal body, your immune system, that's going to protect you from the disease, not from the infection, but from the disease. And vaccines are not all equivalent. And as you know, as we'll see in a later slide, there are many types of vaccines that are now being developed. And it may be, ultimately, that we need a combination of these vaccines to fully protect us. Next slide. I think a question you should begin asking is, are you going to get vaccinated once there is a proven, safe, and effective vaccine? You need to think about that. Next slide. So in terms of vaccines, we have, as of yesterday, 34 candidate vaccines that are in clinical trials and 144 candidate vaccines that are in preclinical trials. Will one vaccine be sufficient? Probably not. We're probably going to need several different types of vaccines. But to get started, one vaccine is probably what you're going to get, hopefully within the next 6 months, but we'll see. Next slide, please. So why would you get vaccinated? I asked if you would get vaccinated, but why would you get vaccinated? Well, for one thing, for this current crisis, you want to protect yourself. But in many cases, vaccines given across a population are important for reducing the occurrence of the virus and the spread of the virus. The next slide, please. This is about public health, and public health is about protecting not necessarily individuals per se, but rather protecting populations. If we can get a very large fraction, and no one's clear exactly on the numbers, but they're probably between 75 and 85% of the population protected, then the transmission rate of this virus will drop very significantly, because it won't be able to go from one person to the next like it can do right now, because we have no immunity. Next slide. So this is I don't want you to think that this is a political statement. This is a slide that I made. I did a TED talk at West Lafayette High School during the Zika pandemic. And it was, what should you expect from government and health leaders to protect you from infectious disease? We want to have a surveillance network to look out for outbreaks before they hit a large fraction of the population. We want to be prepared. We want to have that personal protective equipment. We want to have everybody ready when something does occur. We want to have a single voice to be able to advise the population on what to do, and we want to be able to protect people as much as possible. This is what we need. That's what we expect from the Centers for Disease Control and the National Institutes of Health. Next slide, please. I just want to throw this fact out. We're coming to the end of my short presentation, but I just want to tell you that there's a significant, this is before COVID, significant fraction of kids in the United States are not vaccinated against childhood diseases. The wealthier you are, the more likely it is that your children will not be vaccinated. If you are educated with college degrees, it's more likely that you won't have your kids vaccinated. Where, I can ask, in what county in the United States has the highest rate of unvaccinated children? And you would probably never guess the answer. The answer is Boulder, Colorado. Boulder, Colorado also has one of the highest number of PhDs per capita in the United States. What country in the world has the highest rate of vaccination of their children? It's Bangladesh. Those people know what infectious disease can do to them. And if we have a vaccine, they want it. France is the country that has the lowest rate of vaccination. Just a little tidbit for you folks. Next slide, please. So what can we do to eliminate this infectious disease? And this is true for Zika. It was true for Zika. It's true for COVID-19. We need to understand a little bit about the virus. We need to understand how it's transmitted. And then we have to modify our behavior so that we're not doing things that are going to be conducive to transmission. If there is a vaccination strategy, if there is a treatment, we need to think about that and very seriously get some. And it's very important, even though public health is about populations, every individual contributes to public health. And so your role in eliminating infectious disease and COVID-19 is really important. Okay, next slide. I just want to conclude by telling you some things. There's lots of things that are going on at Purdue. Lots of faculty and students are working on a variety of different projects. Andy Messakar and Arun Ghosh. Andy is in biochemistry and Arun Ghosh is in chemistry. They've actually been working on SARS viruses for 15 years. And Arun is a chemist and Andy is a structural biologist. And they've been working very hard. Next slide, please. I won't bore you with the details, but they have developed some very potent molecules that in vitro, that is in a test tube, inhibit COVID-19 very significantly. And I'm lucky enough to work with them. On the next slide and last slide, we have a facility at Purdue that is a high containment laboratory, which we call a BSL-3, Biosafety Level 3. And these are two of the researchers in my group who are testing some of the compounds that Professors Ghosh and Messakar have produced. And so we're very much hoping that we can directly contribute, in this case, to the therapeutics that we're going to need, regardless of the vaccines. We're still going to need a lot of therapeutics given the penetrance of this virus. So with that, I'm really excited to answer your questions. So thank you.
Great. Well, hey, thanks much, Richard, for giving us that overview. Again, if you have some questions you would like to hear Dr. Kuhn respond to, please do enter them into the comments section. I did have questions that folks had provided ahead of time, and I'm going to jump right in. One of the points you made, Richard, was how this particular virus does affect individuals of different age categories differently. And it seems especially dangerous, and I'll honor Sally Segrist's comment here, to more mature individuals, okay, and individuals with prior health conditions, and it's maybe less dangerous for younger, healthy people. Are we starting to understand why? I mean, what is it about this particular virus that is giving this kind of impact depending on age?
Yeah, first of all, I don't think we have a clear answer on why. It's not unusual for viruses to affect different age groups differently. The immune system is different. You're in a developmental stage, although you might say, well, college kids don't seem to get serious symptoms. I think there's some watch outs with that. Yes, it's a percentage number, and that's important. But we are only 9 months into this disease. We don't know whether kids who are young, just to answer Sally's question, even though they don't show symptoms, even though they don't get sick, we don't know whether there's going to be a long-term effect on them. Maybe there's some effect on their immune system. Maybe there's some effect if they see the virus a second or a third time. So I think it's really too early to say there's no problem with the young kids, and we have to worry more about a little older group of individuals. We really don't know that. And having said that, we don't know in anybody who is actually going to get sick. Yeah, there are certainly indicators, obesity, high blood pressure, diabetes. These have effects on the immune system, and therefore it may simply be that your immune system is not able to work directly as well as with someone who doesn't have those things. So it's not clear whether it's always the virus. It may be much more your immune system, and certainly some of the proteins and other features that make you unique, because young people do get sick. Mm-hmm. And why do they get sick and other young kids don't get sick? And there's certainly folks my age, I won't say age, but who are in a higher risk category that don't get sick or don't even show symptoms. So I think we don't know enough. We have to wait a few years to really understand that question. It's a very important question.
Mm-hmm. So another point you talked about, one of your slides picked up on, was how this particular virus is spread. There's stories of aerosol spread through flushing toilets, and it does seem especially contagious. Is it, and why so? I mean, wonder if you might talk about just the transmission of the virus.
Yeah, it's a respiratory virus. And so, we all breathe, we all talk. Some of us talk louder than others. Some of us have a little spit when we talk. some aerosolize more. Think about viruses that affect cruise ships. These are neuroviruses. Those viruses are very good at spreading. They are fecal oral, so gastrointestinal type virus. They're very efficient at spreading. That's probably more because of contaminated surfaces and our tendency to put our hands near our mouth. Here's a virus that can go without a direct connection from me to you. And so that makes it pretty contagious. And there's other features, biological features, that make it infectious. Okay, so it's both easy to be transmitted, and then once it's on somebody or in somebody, it has a high frequency of initiating a successful infection.
So we talked a little bit about the whole issue of the number of cases, and as we've gone through the last several months, it looks like cases have gone up. In some situations, death rates have gone down. So people don't seem to be, it doesn't seem to be fatal in as many instances. I mean, are we seeing better treatments? I mean, what's going on there as we've learned more about this virus with respect to how deadly it might be in certain situations?
Yeah, I think we've learned a lot about how to treat it, and so that's one of the major reasons why you're seeing a decrease in mortality. Physicians are able to treat the virus more effectively. There's not a lot of antivirals right now, but certainly support for the infection, I think, has gotten substantially better. If you look at the statistics, how many people have been hospitalized, that's a lot of people. And so we've gathered where they've done it. We've gathered a lot of information on how to do it better, how to keep people, safer in the extreme forms of illness.
Mm-hmm. Are there any particular approaches that seem to be, most promising on the therapeutic front from your standpoint?
I think the therapeutics are going to be coming in parallel with the vaccines. The therapeutics, though, as I said before, you really want a vaccine because you really don't want to get it and have to take an antiviral. Okay, you want to prevent it, and right now we don't have the vaccine, and so the masks, the social distancing, and those are important components to prevent the disease. Once we have a vaccine, that'll be another layer of prevention. But we will have antivirals more than remdesivir probably in a few months. There's lots of things going on. I talked a little bit about the work that Professors Messakar and Ghosh are doing. These are all leading, I think, down a pathway in which we'll have quite a number of pretty reasonably good antivirals.
So you talked a little bit about the notion of immunity, but specifically, what do we know about that? If I am COVID positive and recover, will I get the disease again? I mean, what do we know about that sort of potential, I guess, of getting reinfected?
Right. So there's been 6 million infections, right? And we only have one well-defined case of a kind of a reinfection. So I think we're unsure about that. The more important question that is related to that, Jay, is the vaccine. We're now putting these several vaccines are in phase 3 clinical trials, which means that they're in vaccinating 10, 20, 30,000 people at least, and in diverse communities, probably stratified by age. We're going to, first of all, there's safety questions, and safety tests are done in phase 1 and phase 2. We're going to get real good safety information now for phase 3. We're putting in a lot more people. We know that most of these are eliciting pretty good immune response. But the major question, there's two questions. The major question is, if you mount an immune response that we measure, in a laboratory, does that translate into protection when you are outside and encounter someone who is COVID positive and they transmit the virus to you? Will you be protected from disease? That's the major question. Then the second one that's related to that, let's say the vaccines look good, they protect. how long is that protection going to be good for? And let there be no doubt, we are not going to know that answer in 3 months. We probably will not know that answer in 6 months, maybe in a year. It really depends upon the dynamics of the pandemic, how well we're going to know that. But that's the more important question. Once you get vaccinated, how long is that protection good for?
And one question again for an economist who's asking questions of you today. You talked about it may be multiple vaccines that ultimately become the way that we deal with this virus. Is that a vaccine that's got multiple elements, or is it multiple shots? I mean, how does that play out from a treatment or a prevention standpoint?
Yeah, well, we don't know right now. It's one vaccine. You're going to get one vaccine. You're not going to get a cocktail of vaccines. We don't know enough about the immune response and what is considered what we call protective immunity. Protective. It's one thing to get antibodies, but it's another for those antibodies to work effectively and for your immune system to work coordinately against this pathogen. And so we're probably going to see one vaccine that you're going to get. There's probably going to be multiple vaccines that are going to be available in 6 months or whatever. But it's probably more down the line. It'll be second generation or third generation vaccines that if necessary, maybe it won't be necessary, but if necessary, will have multiple components to stimulate the immune system.
Okay, great. Yeah. So while we're on this topic, I want to pick up a question from Jessica Redmond. Again, she appreciates you being here, but what's your best guess for how long we're going to be wearing masks and altering our social activities due to COVID-19?
Yeah, I think until we have a vaccine that is widely distributed, and so that was my push on public health, that we really need a large fraction of the population to be protected. Remember, there are always going to be people who are immunocompromised or have other health issues who may not be able to tolerate a vaccine. And so for the sake of those folks and for the sake of the people who haven't been vaccinated, it would be good if we have what has been called herd immunity. That is, sufficient number of people have protection and are protected against the virus, so that if I get the virus, I've been vaccinated, I get the virus, I don't get any disease, and importantly, I'm not going to spread that virus to another person.
And you talked a little bit about that earlier. And
I guess, Jay, let me just go back to Jessica's question. We don't know what that time frame is going to be. My best guess is probably 6 to 8 months. It really depends upon how fast the vaccine is distributed and how many people take the vaccine. If the number is that people have thrown out, that only 50% of the people are going to get vaccinated, then we're going to have a problem, because we're going to have continuing infection.
So maybe while we're on the topic of vaccines, got another question from Jen Million. Can we be confident that a vaccine introduced this year in 6 months is safe and effective?
That's a real good question. There is a process that has been done for many different vaccines. It's a proven process. It's not 100% safe, but it's as safe as you can get. There's not much in the world that is 100% safe. So I have some level of confidence, probably a fairly high level of confidence in Tony Fauci, and the FDA will have an independent board that will help evaluate these vaccines. I think, you hear all of the numbers. I think it's unlikely that we're going to see anything by November. Even December, it's going to be tough, because I think most of these vaccines require 2 doses. 2 doses spread usually 3 to 4 weeks apart. So even if they're only enrolling people now, it's still going to be another month or two. The important thing about the clinical trials is that you have to have a reasonable number of people normally exposed to the virus. So you have to have high levels of virus transmission in a community in order to assess whether the vaccine is doing its job. And that's done using a lot of statistics. And I know a lot of my colleagues look at those statistics very carefully. And that's what will be used to determine whether a vaccine is safe or not. So we have to have confidence in the science, because the science is based on a lot of experience. We just have to hope that there's, the politics kind of stay out of this. There's no doubt everybody wants a vaccine, but everybody wants a safe and effective vaccine. And we have to wait until the experts say this is safe and effective.
So we got several questions related to testing, Richard, before the session, and I want to ask a few of those. But the first question was, please elaborate on the difficulties in testing. Why do we see so many differences of opinion of when to test, different testing methods, their reliability? So could you comment on that sort of generally about testing?
Yeah, it's kind of a complicated situation, because we have geared up very rapidly for COVID-19. The normal test, which is called a PCR test, that is looking for copies of the viral nucleic acid. In this case, it's RNA. So the genome, we call it the genome. That usually signifies that you have the virus and that it's probably replicating. Now, I think Dr. Hagen sent you, Jay, a question.
Right.
And his question really was, the PCR test is a plus or a minus test. And that's true. It says either we detect nucleic acid or we don't. If we detect nucleic acid, there's a real question of how much. How great is the infection? Are we on the front end of the infection, or are we on the back end of the infection? The test doesn't give us that information because it's not a quantitative test. And so it's not super useful. I mean, it's useful for saying, yes, you probably are infected. Yes, the virus is there, but we don't know a lot about it. We don't know how that can translate into a treatment, for example. So, I mean, they have the technology to do that. It's just that it would be a far more expensive test, and it would take more time to run those tests. Right now, we want to know pretty quickly whether you're infected or not. So, but for any test, there is an error involved. And just think about, if you have to have a nasal swab done, what is the efficiency of collecting the same amount of material from one person to the next? There's variability when you do that kind of thing. If you have to spit in a tube, trust me, some people are big spitters and some people are little spitters. Okay, so there's variability in samples, and then there's variability all along the chain. Now these tests are designed to minimize those things, but there is variability in that. And that's only the PCR test. There is also what we call an ELISA test. An ELISA test is looking to see whether you have antibodies against the virus. Antibodies are not going to say whether you have an active infection. It's going to say whether you've previously been infected with the virus. So there's different tests and different tools that can be used to assess exactly where you are in infection.
So, I mean, just staying on that one, what the potential for even faster and more accurate tests? I mean, I know there's an incredible amount of work being done on vaccines and therapeutics. I assume lots of work done on testing to make that process more accurate, faster, cheaper, et cetera. I mean, do you see developments coming there?
No, there's tremendous amount of work going into diagnostics. We at Purdue have 3 or 4 groups that are moving their tests along, so we're doing really well. I think the answer will ultimately be to have 2 tests done, and those 2 tests have to come up with the same conclusion, and hopefully they give you slightly complementary information. And so, yeah, I think we'll see that very soon because these tests are being optimized, more efficient, cheaper, and more reliable, more accurate. So I think we're probably there in another month or two in terms of having a whole battery of tests, diagnostic tests. Testing, of course, is the important thing because testing is the way that we can make sure that one person who might be infected doesn't transmit it to 15 other people.
Absolutely. And I think this was another Dr. Hagen question. How do we educate the public that all COVID-19 tests cannot distinguish between live and dead virus? Just because you have a positive test doesn't mean you're infected. I mean, do you want to comment on that point?
Yeah, and that goes back. I mean, the tests that are being done are looking for this nucleic acid, which is an indicator that the virus is there. But as Dr. Hagen said, the virus may be dead. It might not be replicating, and we still detect it as a positive signal by this PCR test. Okay, so ultimately, we'd like to understand: is the amount of RNA, the test that we're getting, is it going up, is it flat, or is it going down? That would be the indicator of exactly where we are in the infection process.
Got it. So question, and it gets to your point about positives and negatives and errors, but the question was, why are the numbers not being reported showing the relationship between those being tested and those showing positive or negative? It's an important relationship showing true trends. The more you test, the more chance of showing high positives.
Yeah, and that's absolutely important. We need to know what the positivity rate is. State of Indiana does report positivity rates. Not everybody does, but that's the important thing, whether you're high on that number or low on that number. That is, every person that has some thinking that they might be infected, are they infected? Mm-hmm. So, but there, I think there is a reasonable number of places that are reporting positivity rates.
So, and I think we've answered this one, but I'll ask it anyway because someone did ask it. Can you comment on testing, where it's going? Will we be testing for the virus differently in 6 months or a year? And if so, what might that look like?
Yeah, I think in 6 months, I think it'll be an easy test that you do at home. It'll be recorded on your phone, sent to your doctor. As I said, ideally, I'd like to see maybe 2 tests that look at virus in a different way, so that they're complementary, so that you have a high confidence that they're giving you an accurate answer. There's always these false positives and there's false negatives. And so we want to make sure that those numbers are far more accurate. And I think we're getting there.
So Stephanie Henslow's asked a question here, and I'll read it. If there is an inevitable flu virus in our near future with similar effects on our global social interactions, it seems likely that our current way of life, masks, social distancing is here to stay from now on. The new flu strand would need new vaccines. The process restarts. Do you believe that to be true?
I hope that it's not true. I mean, I can't say with certainty, but we have experience with flu. If there is a pandemic flu virus, and let me just tell you how a pandemic flu virus is going to occur. Normally, the seasonal flus that we have, these are moving. They're probably, we can see them in birds, we can see them in people. They don't change much. There's some strain changes, but we don't see much variation. And so we make this cocktail. There's usually 3 vaccines, 3 different viruses we make the vaccine against in the spring of the year, and then that's what the vaccine you get in the fall. If there is a pandemic flu virus, we would probably have to redo that process very quickly. And that will be a challenge, because the bottom line is that we don't have full capacity to vaccinate the world for flu. Even in the United States, I don't know what the numbers are, but not everybody gets vaccinated against flu. And I'm not sure that we even have the capacity to vaccinate 330 million people should they want a flu vaccine this year. Okay. So that's the real challenge. Yes, if there is a pandemic flu virus, we will be back to wearing masks. There's no doubt about it. But hopefully, we would be able to develop a vaccine and implement it fast. One of the challenges with this virus is, as I've kind of been suggesting, we don't understand all of the features of the virus so that we can make an effective vaccine. We're hoping we know, but we're not sure because we've only seen this virus for 8-9 months. The flu we know a lot about, and I'll just tell everybody that a few years ago, in order to understand why the 1918 flu was so dangerous, so deadly to people, people were able to recreate this virus. It was done under a very high containment, but they were able then to dissect out what are the features of that virus that made it so deadly. So we have a lot more information about flu and how a pandemic flu virus would emerge. And back to one of my slides, the important thing that we must maintain is surveillance. And with surveillance, it's not just the United States being, surveilling for flu. We need, and we have, a global network of people around the world who are looking at what viruses are circulating primarily in birds and in some domestic animals. And that will be the kind of the warning sign, kind of the sentinel chicken, if you will, for a pandemic flu.
I think we vaccine development, realistic timeline, and any that look especially promising was the question.
Yeah. So quite a number of the vaccines that have moved into clinical trials are being done with a strategy that has never been used before. That's nothing to particularly be worried about, but there might be things that we've not anticipated. But this strategy that's being used by some of the leading companies that are pushing their vaccines forward is one in which there's no virus involved, and it's only a component, and the component is being synthesized by your body's own cell. So it's a very different strategy. It's one of the reasons why many companies could rapidly develop these vaccines and move them forward so fast. I think those probably will be kind of the leading edge of the successful vaccines. Some of the other vaccines use a virus as a vehicle. They use a modified adenovirus as a vehicle. Those are also moving forward. And the reason why they can move forward is that we have experience in working and developing them as vaccines. So we have enough knowledge about the vaccine production process that we can move forward. It's really a matter of a clinical trial demonstrating safety, demonstrating immunogenicity, and demonstrating, most importantly, protection. And that's something that we can't rush. So I think, we'll see vaccines probably emerge in the beginning of 21. It's then a question of getting them pushed out to, hundreds of millions of people in the United States, billions of people worldwide.
And to your point, we just saw an example, I guess, of the kind of challenges that can happen in a clinical trial with this AstraZeneca vaccine. And one patient that showed symptoms that were unusual, they halted the trial or paused it, I guess. I mean, if that's correct.
Yeah. First of all, we don't know what the symptoms were. We don't know whether that person was in the placebo control group or whether it was someone who actually got the vaccine. If you give 1 million people a needle injection of saline, some people are going to have a reaction to it. I mean, this is just probability and the complexity of the human body. And so there are bound to be adverse reactions that may have nothing to do at all with the vaccine. They may, in which case we really need to understand what's going on. Again, this is why you do it in a diverse population. It may be specific to a particular type of person who had the adverse reaction. It could be in a person who has hypertension. We just don't know the details of that, but that's why you do these very large clinical trials to see. In fact, I wouldn't say you're hoping for adverse effects, but you want to do a clinical trial. And you want to be confident at the end of the clinical trial that you're going to give it to millions of people and you're not going to see those adverse effects. So in fact, if there's a problem, you do want to see the adverse effects early on so that you can figure out what's wrong.
Sure. So you talked a little bit about this in your presentation too. So long-term health effects of COVID-19, some have offered up, if you're asymptomatic, you may not see the damage the disease has done, for years. Just wondering if you might comment on that. I'm sure there's so much we don't know about a question like that.
Yeah. I mean, if we think back about Zika, the whole outbreak, and it was also an epidemic, close to a pandemic. The whole thing was that we were seeing children who had malformed heads, brains. And that was kind of the signature for Zika infection. But that was the extreme case. That was in that pyramid of pathogenesis that I showed you. It was the very peak. There certainly were kids, or there were mothers who were infected with Zika and delivered a child that looked normal, was normal, but a few years down the line, there are some developmental issues because the virus did replicate in certain cells in the brain and caused some damage that you only detect further down the developmental pathway. So I think we really have to wait and see whether we're going to see similar type things with COVID-19 in people who are infected and don't show any obvious symptoms. It's an important thing that we need to be watching out for. But it may only express itself 5 years from now or 10 years from now.
So we've got a couple other questions from folks that sent in prior to the session we get to in the last few minutes. Regarding COVID-19, what will the conversation sound like in 5 years? Will we talk similarly about COVID-19 as we do about influenza A and B?
Yeah, well, I think we've all had, this is our flu pandemic of 1918. It's our COVID pandemic of 2020. We will remember the impact. Hopefully we all will remember that we could have been better prepared, that we should have had better things in place to deal with it. And then that's at every level of our society, not just the kind of scientific medical side. I think that COVID-19 will fade and that hopefully we will push it out. I don't think we can't eradicate it because it's coming from animals and there might always be an animal reservoir. And if we don't have everybody vaccinated, there's still going to be potential infection. But I think unfortunately, we need to always be thinking about the next outbreak. It seems that in the last 20 years, there has been a cycle of every 2 to 3 years, there has been an outbreak of some significant viral pathogen. We've seen Zika, we've seen Ebola, we had MERS, we had SARS, we have COVID-19. We've been through quite a bit. And so there's no reason to believe that won't change. It's a question of will we be prepared and can we stop the virus before it spreads regionally, globally.
So maybe last question, could you just comment generally on the response of the scientific community to this virus? I mean, to an outsider, it feels like just an extraordinary global response to looking for therapeutics, for looking for vaccines. But I just wonder how you, as a scientist, how you might characterize that response.
Yeah. So, all of my colleagues that I know of, except for the plant virologists, perhaps, they're all kind of retooling and doing some aspect of COVID-19, in part because they have particular areas that they work on that can be translated over to this virus. And so it's been an enormous shift in the virus community to work on this thing. But I think, Jay, you know this well. There are many faculty at Purdue who have picked up the torch and have started working on COVID-19. And this goes across the spectrum of disciplines. The ones you expect, and then the ones you don't expect. The humanities and engineering and obviously nursing, public health. I mean, there is a huge effort on the part of Purdue and many universities to really put their brain power to good use here. So it's been fun. It is very competitive. There is papers flying off the shelves. And so it's difficult to always assess how good some of the science is. That's I think one of the challenges.
And of course, the private sector has poured incredible amounts of money into this, as well as governments. So it's just been, kind of the global full court press on this.
Yeah, and there's been great collaboration between academia and companies. A lot of the vaccines are kind of joint efforts amongst groups. So it's really good to see.
Well, we're drawing to the close of our time this afternoon, but I know if you were joining us today, you appreciated the remarks and insights of Dr. Richard Kuhn, bringing us a virologist perspective on COVID-19 and some of the particular nuances of this disease, where we may be going with vaccines and therapeutics, and just more broadly how these pandemics unfold and some of the root causes. So it's we're fortunate in this community to have experts like Dr. Kuhn who can bring us these kinds of insights, and appreciate United Way of Greater Lafayette for sponsoring this series. Hope that you'll be able to join us again the next few weeks as we open up some other topics. And again, we'll come back to where we started. We just want to say thank you for your contributions, your investments in United Way, especially at this particularly important time. And we hope that you, as donors, will continue to support United Way financially, but also you'll encourage others, especially this year, to invest in the United Way community campaign. So again, thank you very much for joining us this afternoon, and again, have a great rest of your week.